The objective in this analysis is to take a stack of images that clearly contain a very nice structure from a molybdenum 3D and sulfur 2s and use these to help analyze the peak composition that lies beneath such a complex envelope as this. So we'll begin first of all by actually reducing the number of images that we're going to analyze by simply offsetting one set in terms of the column in the right hand side. I'll call that B. Press OK, and you can see that we then get a movement of the every other VAMAS block to a second column, and this one here will still contain sufficient information when I display the spectrum generated from this using all of the pixels. So I'm summing all the pixels, and the step size is sufficient to keep a well-formed spectrum, even though I've discounted half of the acquisition. And this will help us to compare the process versus the raw data, because I can simply select these and overlay them to see the corresponding spectrum from the next set of images. So let's go back here to the first column, and I will now select not a box. This box here is summing all the pixels within it. I'm now going to select a single point. So this is what a spectrum looks like at this point here. So if I select the second column overlay, you can see there's another noisy spectrum. So let's go back to the one we're going to process. And the first thing we'll do is we'll go to the outlier filter option, give it 90% and 5 iterations, and this will just clean up the unusual pixels within these images and help to create what you can now see a slightly more obvious spectrum. You've got a couple of peaks here and another one forming here, so even just doing an outlier filter has cleaned up the spectrum immensely. And now let's go to the options on the image processing page. I'm going to select to calculate 10 abstract factors, and I'm going to use 8 of them to reconstruct the data. I'm working on the basis that there will be more than or less than 8 abstract factors that are significant to the data. So I press this button here, and when I recreate this data set using 8, then I will include some noise in the spectra. So as you can see, there's an element of noise here, but clearly now at a pixel we have a spectrum which is quite obviously the molybdenum disulfide with some molybdenum oxide mixed in there as well. And if I now overlay the unprocessed data that are offset by 0.1 of an EV, you can now see the comparison between a unprocessed form and the process form. So let's use the process form and create some spectra. And here I can once again, this is a set of VAMAS blocks. Each VAMAS block contains a row of spectra corresponding to the data in the images, and if I step across by holding the control key down, we can see these spectra that are within these VAMAS blocks. Alternatively, what we can do is we can go over here and say convert the corresponding variables, and that's where all these spectra are stored, to individual VAMAS blocks. So when I do this, I create not a column of VAMAS blocks but an array of VAMAS blocks, and within each VAMAS block there's an individual spectrum. And again I can move around, and you can see that we've got, although they are not perfect spectra, we've got 16,000 spectra that are showing us the relationship between the molybdenum disulfide and the molybdenum oxide that's on the surface. So I'll close that because that was just to illustrate the number of spectra that are genuinely underlying these measurements. And the thing that we would like to do is get a rough idea of the distribution of these different materials, the oxide versus the sulfide with the molybdenum. So let's first of all just put on a background. So we have we'll just use a basic Shirley background for this analysis. And if we then create another region, I can then adjust that region to span one of these peaks. And if it calculates the Shirley background, it's not going to be very good approximation. So what I'll do is I'll put skip. So it doesn't calculate a background, but it'll use whatever background went before. So this Shirley background here is now the one that's being used for this peak, this region here, and this is going to be oxide. Now I'm going to create another one, and it's going to remember that I used skip before. I'll just put that an average width of 0, since it actually has no effect on the skip background. That's just related to the Shirley, and I might as well actually make that 2. Give it a bit more stability at the ends of the region, defining the background. And this third region I'm going to slide across, and this one is going to be located on this doublet peak, and that one I believe to be a combination of the oxide and the sulfide. And one more. And this one is going to be positioned across the 5/2 peak of the molybdenum 3D, and that one is the sulfide. And then I can do one more, which will be the sulfur 2s. Now I'll mark that as sulfur 2s, why not? And if I now propagate these regions to all of these VAMAS blocks, I get a background, and I get these regions on each one of these VAMAS blocks, which I can then use to create images. So for each region that I've got defined here, I'm going to create an image, and from these images I will be able to create atomic, or rather percent area images. So let's convert regions to images, and now we have a set of images. We've got one for each region that was defined. This one's the total. This is the oxide. This one is the combination of oxide and sulfide. That's the sulfide, and that's the sulfur 2s. So we'll just use these images here, and we will then quantify. That means we're going to divide by the total area. So now we've got an oxygen bonded with molybdenum. That's the combination of the two, and that's the molybdenum that's bonded with sulfur, and there's another one. So we'll go with this one here as a measure of the distribution of molybdenum disulfide, and this will represent the molybdenum oxide. So let's copy that, so we can work on it a bit without interfering with the original image. And what we'll do is we'll just apply a few smoothing operations here, and the idea is actually to try and unify the intensity associated with these different zones. So there's sulfide, oxide, and what I want to do now is go to the false color, and I'll mark out the intensities over which I want false colors to be defined. I'll use a bicolor, use histogram equalization. We'll go with 6 colors and press OK. So now we get a set of colors that have been assigned to the pixels in this image, and each one of these colors can be used to sum spectra. So what we'll do is we'll define that as the mask that's going to be used in the analysis, and what we'll do now is we will look at raw images and take raw spectra, and we'll sum these raw spectra using those false colors, and that gives us a set of 6 different spectra calculated from those different intensities. So these two, this one and this one, ought to be very closely associated with an oxide, and these two ought to be very closely associated with a sulfide, and you can see that the sulfide peak is much larger here than it is in these two peaks. So what we'll do is a little bit of analysis based on manipulating these intensities as vectors, and the first thing we'll do is add a couple of these together that we can see make sense in terms of one form and the other. And the idea we're trying to improve signal to noise. When you do manipulation of these as vectors, noise tends to be amplified, so it's always a good idea to have the best signal to noise that you can achieve with data. So I've got two spectra here, one that favors the sulfide, one that favors the oxide, and I'm going to go onto the calculator property page, and I'm going to send 0.2 for my factor between these different spectra that I now calculate. And if I step down here, let me just close these dialog windows, you can see, let me just also put up a display so it's obvious what's happening. But with each step the spectra change, and I'm now subtracting these data and displaying the different spectrum to the point that I can now see that I'm getting something that looks like it's got predominantly molybdenum disulfide and some sort of perhaps some oxide here. But that'll do for a first approximation, so let's take that one and I will copy that, and that gives me my first spectrum that might be of interest. And now I think I like this one also, so I'm going to copy that one. And then we'll keep on going down, and you can see that the contribution of the oxygen is starting to go negative. And the idea is that what we're going to find now is a peak shape, an envelope structure that might just give us an alternative perspective of these data. And I think that one might do it, so let's copy that one. Okay, so I've got three spectra that I've calculated, and I think we'll go with these two. And I'm going to move these back to the lookup table spectra, so that I've got these as two basis functions that I can put into here, and I can see how these now can be used to decompose the rest of these spectra that I didn't use in the calculation. So I use these two to calculate the different spectra, and now I am applying a least squares principle to create a set of approximations to the original lookup table spectra. So the first lookup table spectrum that was mostly oxide contains a proportion of this spectrum and a proportion of this one, and so we have a pretty good approximation. The black and the red are the original, is the black, and the red is the sum of these two component spectra. And if I go down, you can see that of the 6 lookup table spectra that I extracted from those images, I've now got good approximations to how to decompose these complex envelopes into these less involved envelopes. That has very much the structure of molybdenum disulfide, and this one looks like molybdenum trioxide maybe, and some other form.